In the Foundations of Mathematics, von Neumann Bernays Gödel's set theory is an axiomatic set theory that is a conservative extension of the canonical Zermelo Fraenkel set theory. A statement in the language of ZFC is provable in NBG if and only if it is provable in ZFC. The ontology of NBG includes proper classes, objects having members but that cannot be members of other entities. NBG's principle of class comprehension is predicative. Quantified variables in the defining formula can range only over sets. Allowing impredicative comprehension turns NBG into Morse-Kelley set theory. NBG, unlike ZFC and MK, can be finitely axiomatized. Ontology. The defining aspect of NBG is the distinction between proper class and set. Letter in SB2 individuals. Then the atomic sentence is defined if A is a set and S is a class. In other words, is defined unless A is a proper class. A proper class is very large. NBG even admits of the class of all sets, the universal class called V. However, NBG does not admit the class of all classes, or the set of all sets. By NBG's axiom schema of class comprehension, all objects satisfying any given formula in the first-order language of NBG form a class. If a class is not a set in ZFC, it is an NBG proper class. The development of classes mirrors the development of naive set theory. The principle of abstraction is given, and thus classes can be formed out of all individuals satisfying any statement of first-order logic whose atomic sentences all involve either the membership relation or predicates definable from membership. Equality, pairing, subclass, and such are all definable and so need not be axiomatized. Their definitions denote a particular abstraction of a formula. Sets are developed in a manner very similarly to ZF. Let Rp, meaning the set A represents the class A, denote a binary relation defined as follows. That is, A represents O if every element of A is an element of A, and conversely. Classes lacking representations, such as the class of all sets that do not contain themselves, are the proper classes. History. In two articles published in 1925 and 1928, John von Neumann stated his axioms and showed they were adequate to develop set theory. Von Neumann took functions and arguments as primitives. His functions correspond to classes, and functions that can be used as arguments correspond to sets. In fact, he defined classes and sets using functions that can take only two values. Von Neumann's work in set theory was influenced by Cantor's articles, Zermelo's 1908 Axioms for Set Theory, and the 1922 critiques of Zermelo's set theory that were given independently by Fraenkel and Scholem. Both Fraenkel and Scholem pointed out that Zermelo's axioms cannot prove the existence of the set Z0, Z1, Z2, where Z0 is the set of natural numbers, and Zinc plus 1 is the power set of zinc. They then introduced the axiom of replacement, which would guarantee the existence of such sets. However, they were reluctant to adopt this axiom. Fraenkel's opinion was that replacement was too strong an axiom for general set theory, and Scholem only wrote that we could introduce replacement. Von Neumann worked on the deficiencies in Zermelo's set theory and introduced several innovations to remedy them, including a theory of ordinals. Zermelo's set theory does not contain Cantor's theory of ordinal numbers. Von Neumann recovered this theory by defining the ordinals using sets that are well ordered by the relation. In contrast to Fraenkel and Scholem, von Neumann found the axiom of replacement so essential to his work that he declared, "In fact, I believe that no theory of ordinals is possible at all without this axiom, a criterion identifying classes that are too large to be sets." Zermelo did not provide such a criterion. His set theory avoids the large classes that lead to the paradoxes, but it leaves out many sets, such as the one mentioned by Fraenkel and Scholem. Von Neumann's criterion is, a class is too large to be a set if and only if it can be mapped onto the universal class. Von Neumann realized that the paradoxes can be avoided by not allowing such large classes to be members of any class. Combining this restriction with his criterion, he obtained his axiom of limitation of size. A class 10 is not a member of any class if and only if X can be mapped onto the universal class. He proved that this axiom implies the axioms of replacement and separation, and implies that the universal class can be well-ordered. Finite Axiomatization. Fraenkel and Scholem formalized Zermelo's imprecise concept of definite propositional function, which appears in his axiom of separation. Scholem gave the axiom schema of separation that is currently used in ZFC. Fraenkel gave an equivalent approach. Zermelo rejected both approaches, particularly because they implicitly involve the concept of natural number which, in Zermelo's view, should be based upon set theory. Von Neumann avoided axiom schemas by formalizing the concept of definite propositional function, with his functions, whose construction requires only finitely many axioms. This led to his set theory having finitely many axioms. The axiom of regularity. Zermelo's set theory does not exclude non-well-founded sets. Fraenkel and von Neumann introduced axioms to exclude these sets. Von Neumann introduced the axiom of regularity, which states that all sets are well-founded. Although von Neumann did not adopt regularity as an axiom, he proved its relative consistency while studying his axiom of limitation of size. First, he weakened his axiom system by replacing the latter axiom with two of its consequences: replacement and a choice axiom equivalent to global choice. Next, he proved that if this weaker system is consistent, it remains consistent after adding the axiom of regularity. Finally, he showed that his weaker system augmented with regularity proves the axiom of limitation of size. These results establish that the axioms of regularity and limitation of size are relatively consistent with respect to his weaker system, and that replacement and his choice axiom are equivalent to the axiom of limitation of size. In a series of articles published between 1937 and 1954, Paul Bernays modified von Neumann's theory by taking sets and classes as primitives. By using sets, Bernays was following the tradition established by Cantor, Dedekind, and Zermelo. His classes followed the tradition of Boolean algebra since they permit the operation of complement as well as union and intersection. Bernays handled sets and classes in a two-sorted logic. This required the introduction of two membership primitives, one for membership in sets, and one for membership in classes. With these primitives, Bernays rewrote and simplified von Neumann's axioms. He also adopted the axiom of regularity, and replaced the axiom of limitation of size with the axioms of replacement and von Neumann's choice axiom. Gödel simplified Bernays' theory by making every set a class, which allowed him to use just one sort for classes and one membership primitive. He also introduced a predicate indicating which classes are sets. Gödel modified some of Bernays' axioms, and introduced the axiom of global choice to replace von Neumann's choice axiom. He used his axioms in his 1940 monograph on the relative consistency of global choice and the generalized continuum hypothesis. Several reasons have been given for Gödel choosing NBG for his 1940 monograph. Gödel gave a mathematical reason: NBG's global choice produces a stronger consistency theorem. This stronger form of the axiom of choice, if consistent with the other axioms, implies, of course, that a weaker form is also consistent, Robert Solovay conjectured. My guess is that he wished to avoid a discussion of the technicalities involved in developing the rudiments of model theory within axiomatic set theory. Kenneth Kuhnen gave a reason for Gödel avoiding this discussion. There is also a much more combinatorial approach to L, the constructible universe, developed by Gödel in his 1940 monograph, in an attempt to explain his work in On logicians. This approach has the merit of removing all vestiges of logic from the treatment of L. Charles Parsons gives a philosophical reason for Gödel's choice of NBG. This view, that property of set is a primitive of set theory, may be reflected in Gödel's choice of a theory with class variables as the framework. For his monograph, Gödel's achievement together with the details of his presentation led to the prominence that NBG would enjoy for the next 2 decades. Even Paul Cohen's 1963 independence proofs for ZF used tools that Gödel developed for his work in NBG. However, in the 1960s, ZFC became more popular than NBG. This was caused by several factors, including the extra work required to handle forcing in NBG, Cohen's 1966 presentation of forcing, and the proof that NBG is a conservative extension of ZFC. Axiomatization NBG. NBG is presented here as a two-sorted theory, with lowercase letters denoting variables ranging over sets, and uppercase letters denoting variables ranging over classes. Hence, should be read, set X is a member of set Y, and, as set X is a member of class Y, statements of equality may take the form, or, the statement stands for, and is an abuse of notation. NBG can also be presented as a one-sorted theory of classes, with sets being those classes that are members of at least one other class. We first axiomatize NBG using the axiom schema of class comprehension. This schema is provably equivalent to 9 of its finite instances, stated in the following section. Hence these 9 finite axioms can replace class comprehension. This is the precise sense in which NBG can be finitely axiomatized. With class comprehension schema, the following 5 axioms are identical to their ZFC counterparts. Extensionality. Sets with the same elements are the same set. Pairing. For any sets X and Y, there is a set, whose elements are exactly X and Y. Pairing implies that for any set X, the set X exists. Also, given any two sets X and Y and the usual set theoretic definition of the ordered pair exists and is a set. By class comprehension, all relations on sets are classes. Moreover, certain kinds of class relations are one or more of functions, injections, and bijections from one class to another. Pairing is an axiom in Zermelo set theory and a theorem in ZFC. Union. For any set X, there is a set which contains exactly the elements of X. Power set. For any set X, there is a set which contains exactly the subsets of X. Infinity. There exists an inductive set, namely a set X whose members are the empty set. For every member Y of X is also a member of X. Infinity can be formulated so as to imply the existence of the empty set. The remaining axioms have capitalized names because they are primarily concerned with classes rather than sets. The next 2 axioms differ from their ZFC counterparts only in that their quantified variables range over classes, not sets. Extensionality. Classes with the same elements are the same class. Foundation. Each non-empty class is disjoint from one of its elements. The last 2 axioms are peculiar to NBG. Limitation of size. For any class C, a set X such that X equals C exists if and only if there is no bijection between C and the class 5 of all sets. From this axiom, due to von Neumann, subsets, replacement, and global choice can all be derived. This axiom implies the axiom of global choice because the class of ordinals is not a set, hence there exists a bijection between the ordinals and the universe. If limitation of size were weakened to, if the domain of a class function is a set, then the range of that function is likewise a set, then no form of the axiom of choice is an NBG theorem. In this case, any of the usual local forms of choice may be taken as an added axiom, if desired. Limitation of size cannot be found in Mendelssohn NBG. In its place, we find the usual axiom of choice for sets, and the following form of the axiom schema of replacement. If the class F is a function whose domain is a set, the range of F is also a set. Class comprehension schema. For any formula containing no quantifiers over classes, there is a class A such that this axiom asserts that invoking the principle of unrestricted comprehension of naive set theory yields a class rather than a set, thereby banishing the paradoxes of set theory. Class comprehension is the only axiom schema of NBG. In the next section, we show how this schema can be replaced by a number of its own instances. Hence NBG can be finitely axiomatized. If the quantified variables in phi range over classes instead of sets, the result is Morse-Kelley set theory, a proper extension of ZFC which cannot be finitely axiomatized. Replacing class comprehension with finite instances thereof. An appealing but somewhat mysterious feature of NBG is that its axiom schema of class comprehension is equivalent to the conjunction of a finite number of its instances. The axioms of this section may replace the axiom schema of class comprehension in the preceding section. The finite axiomatization presented below does not necessarily resemble exactly any NBG axiomatization in print. We develop our axiomatization by considering the structure of formulas. Sets. For any set X, there is a class 10 such that X equals X. This axiom, in combination with the set existence axioms from the previous axiomatization, assures the existence of classes from the outset, and enables formulas with class parameters, let and then and suffice for handling all sentential connectives, because an are a functionally complete set of connectives. Complement. For any class A, the complement is a class. Intersection. For any classes A and B, the intersection is a class. We now turn to quantification. In order to handle multiple variables, we need the ability to represent relations. Define the ordered pair as usual. Note that 3 applications of pairing to A and B assure that is indeed a set. Products. For any classes A and B, the class is a class. Converses. For any class R, the classes and exist. Association. For any class R, the classes and exist. These axioms license adding dummy arguments, and rearranging the order of arguments, in relations of any arity. The peculiar form of association is designed exactly to make it possible to bring any term in a list of arguments to the front. We represent the argument list as. The idea is to apply association 1 until the argument to be brought to the front is second. Then apply conv1 or conv2 as appropriate to bring the second argument to the front. Then apply association 2 until the effects of the original applications of association 1 are corrected. If is a class considered as a relation, then its range is a class. This gives us the existential quantifier. The universal quantifier can be defined in terms of the existential quantifier and negation. Ranges. For any class R, the class exists. The above axioms can reorder the arguments of any relation so as to bring any desired argument to the front of the argument list, where it can be quantified. Finally, each atomic formula implies the existence of a corresponding class relation. Membership. The class exists. Diagonal. The class exists. Diagonal, together with addition of dummy arguments and rearrangement of arguments, can build a relation asserting the equality of any two of its arguments. Thus repeated variables can be handled. Mendelssohn's variant. Mendelssohn refers to his axioms B1, B7 of class comprehension as axioms of class existence, 4 of these identical to axioms already stated above. B1 is membership, B2, intersection, B3, complement, B5, product. B4 is ranges modified to assert the existence of the domain of R. The last 2 axioms are B6, B7. B6 and B7 enable what converses and association enable. Given any class 10 of ordered triples, there exists another class Y whose members are the members of X, each reordered in the same way. Discussion. For a discussion of some ontological and other philosophical issues posed by NBG, especially when contrasted with ZFC and MK, See Appendix C of Potter. Even though NBG is a conservative extension of ZFC, a theorem may have a shorter and more elegant proof in NBG than in ZFC. For a survey of known results of this nature, see Pudlak. Model theory. ZFC, NBG, and MK have models describable in terms of E, the standard model of ZFC and the von Neumann universe. Now let the members of E include the inaccessible cardinal kappa. Also let F denote the delta zero definable subsets of X. Then, V kappa is an intended model of ZFC. F is an intended model of NBG. V kappa plus 1 is an intended model of MK. Category theory. The ontology of NBG provides scaffolding for speaking about large objects without risking paradox. In some developments of category theory, for instance, a large category is defined as one whose objects make up a proper class, with the same being true of its morphisms. A small category, on the other hand, is one whose objects and morphisms are members of some set. We can thus easily speak of the category of all sets, or category of all small categories, without risking paradox. Those categories are large, of course. There is no category of all categories, since it would have to contain large categories which no category can do. Although yet another ontological extension can enable one to talk formally about such a category, whose objects and morphisms form a proper conglomerate. On whether an ontology including classes as well as sets is adequate for category theory, see Muller.